Good afternoon, everyone. My name is Dartha. Today, me and my groupmates will present about the applications in linear systems in science and engineering. Next. So, to start, what exactly is a linear system? Put simply, it is a set of linear equations that share the same variables and are solved simultaneously. These systems are absolutely essential in our fields because they allow us to model and analyze complex problems where multiple related unknowns must be solved at once. Next.
Okay, so for the first application, I'll talk about force equilibrium in structural engineering. So this topic shows how linear systems are directly used in real structures like bridges and buildings. So basically, we use linear algebra to make sure a structure stays stable and does not collapse. So first, what is force equilibrium? So force equilibrium means that all forces acting on a structure are balanced, so the net force is zero. And when this condition is satisfied, the structure remains stable. And in structural engineering, this is very important because buildings and bridges must safely support loads like weight, vehicle, and or people. Now let's see how force equilibrium turns into math. So in structural engineering, we usually analyze one joint at a time. So let's say at a joint, forces act in different direction. So we split them into horizontal x and vertical y components. For the structure to stay stable, the sum of forces in each direction must be zero. Each of these equilibrium conditions form a linear equation. And from those equilibrium equations, we can rewrite them in matrix form. This is where linear algebra comes in. And instead of solving equation one by one, we combine them into the standard form ax equals to b, where all equations are represented neatly in the matrix. So this makes the system easier to analyze and solve, especially for larger structures. So first, what does ax equals to b means? So the matrix A comes from the geometry of the structure, like the angles of the members. The factor x represents the unknown internal forces inside the structure, and the factor b represents the external load, such as weight acting downward. And when we solve this system, we find the internal forces needed to keep the structure in equilibrium or stable. Now let's look at a real example. Here we analyze a bridge joint where two inclined members met. Each member makes an angle of 60 degrees with the horizontal and a downward load of W equals to 20 kilonewtons act at, at the joint. The structure is assumed to be in static equilibrium, and the goal is to find the internal forces x1 and x2 using force equilibrium and linear systems. And next, we form the equilibrium equations. For horizontal equilibrium, the horizontal components of the force must cancel out. One force acts on the left and the other acts on the right. So their cosine components balance each other. For the vertical equilibrium, the upward components of both forces must balance the downward load of 20 kilonewtons. These two conditions give us two linear equations. And these two equilibrium equations together form a linear system. So instead of writing them separately, we express them in a matrix form, ax equals to b, and this shows clearly how physical equilibrium laws can be translated directly into linear algebra. So after writing the equations, we substitute the known values like sine 60 and cosine 60. And from the first equation, we express one variable in terms of the other. Then we substitute it into the second equation. By solving the system, we obtain the values of x1 and x2. The final result showed that both inclined members carry the same internal force, which is 11.55 kilonewtons. And this happens because the joint is symmetric, so the applied load is shared equally. And since the forces act away from the joint, both members are in tension. And this result matches the real physical behavior of a truss bridge. To conclude this application, in real structures, there are many joints and members. At each joint, force equilibrium produces a system of linear equations. By solving these systems using matrix methods, engineers can determine internal forces efficiently, and that's why linear systems are essential in structural engineering, not just in theory, but in real world design.
In this section, I will discuss the application of linear system using Kirchhoff laws in electrical circuits. Kirchhoff laws are commonly used to analyze electrical circuit with multiple components. When, when circuit become complex, Kirchhoff law allow the circuit to be modeled mathematically as a system of equation because the relationship between voltage and current are linear. The circuit equation from a linear system. Solving this linear system allow us to determine the currents flowing in the circuit. Kirchhoff law consists of two fundamental principles used in circuit analysis. Kirchhoff current law states that the total current entering a node is equal to the total current leaving the node. This law is based on the conservation of electric charge. Kirchhoff voltage law states that the algebraic sum of a voltage around a closed loop is zero. This law reflects the conservation of energy in an electrical circuit. This slide shows the example circuit that will be analyzed. The circuit can consist of resistor and a voltage source and form three loops. To analyze the circuit using Kirchhoff law, we assign three loops current label I1, I2, and I3. The direction of the loop currents are assumed for convenience if a calculated current value is negative, indicates that the actual direction is opposite to the assumed direction. After defining the loop's current, Kirchhoff voltage law is applied to each loop. For each loop, the sum voltage drop across the resistor is equated to the voltage source in that loop. The voltage drop are expressed using Ohm law. We state that voltage equal current multiplied by resistance. Because these are three loops, this process results in three linear equations involving the three unknown loop currents. The equation obtained from Kirchhoff voltage law can be written in matrix form. In this form, the circuit represented as a linear system, the matrix is formed from a resistance value. The unknown are the loop current, and the constant come from the voltage source. Because the voltage current relationship are linear, the entire circuit can be analyzed using a linear algebra method. From Kirchhoff law, the circuit can be modeled as a linear system. By solving this system, we obtain value of the loop current E1, E2, and E3. This value represent the actual current flowing in each loop of the circuit. This step show how solving a linear system produce meaningful physical result in a circuit analysis. This method works because it is based on fundamental physical principles. Kirchhoff's current law ensures current balance through charge conservation. Kirchhoff's voltage law ensures voltage balance through energy conservation. Additionally, Ohm's law creates a linear relationship between voltage and current which allows the circuit equation to form a solvable linear system. In conclusion, Kirchhoff's law provides a systematic method for analyzing electrical circuit. Complex circuit can be modeled as a system of a linear equation, and linear algebra allows the system to be solved efficiently. This approach is widely used in real engineering and demonstrates how physical laws and mathematics work together in engineering.
So for my part, I will be talking about balancing chemical equations. Next. One of the applications of linear systems is chemical equation balancing, and while it could be done by inspection or through trial and error, this could become incredibly tedious and difficult when dealing with complex reactions. So, I'm going to show you how we can use linear systems to balance these equations quickly and with mathematical certainty. Next. So before we get into the math, let's look at the physics. Everything here is based on the law of conservation of mass. This law states that mass cannot be created or destroyed in a closed system. In terms of chemistry, this means the number of atoms for every single element must be identical on both the reactant side, what we start with, and the product side, what we end with. This conservation principle gives us the exact constraints we need to build our equations. Next. Let's look at a real example, the combustion of propane. Here, we have propane and oxygen reacting to form carbon dioxide and water. To solve this, we assign a variable x1, x2, x3, and x4 to each molecule. We then write a linear equation for every element involved. Next slide. Now, look at the system we've created. This is a homogeneous system because all equations are set to 0. Mathematically, we represent this as matrix A. Notice that we have a 3x4 matrix, 3 equations, but 4 unknown variables. Since the number of variables is greater than the number of equations, the system is undetermined. In linear algebra, this tells us that there are infinite non-trivial solutions. And in chemistry, we just need to find the specific set of the smallest whole numbers that satisfy the system. Next slide. So, how do we find those numbers? We start by setting our most complex coefficient, in this case x1 to 1. And then we can just follow the math. If x1 is 1, our carbon equation tells us that x3 must be 3. And our hydrogen equation tells us that x4 is 4. Finally, we substitute x3 and x4 back into our oxygen equation. This gives us x2 must be 5. Our solution vector is 1, 5, 3, 4, which is the set of the lowest possible integers for this reaction. Next slide. Here's our final result. 1 molecule of propane reacts with 5 molecules of oxygen to produce 3 of carbon dioxide and 4 of water. In conclusion, linear systems provide an error-proof method to balance equations while abiding by the law of conservation of mass. The big takeaway is that this doesn't just work for chemistry. Any scientific principle based on conservation, whether it's electric charge in a circuit or the flow of traffic in a city, can be modeled and solved using these exact same linear systems. Next slide. That's all. Thank you for listening to our presentation. Goodbye.